In today's lecture, we will discuss about density of states. What is density? Density is something per unit volume. Okay. What is a state? A state is an allowed solution which satisfies the boundary conditions. Means we have an equation. Okay. Then we applied our boundary conditions, and then when we solve that equation, we get a particular solution. These solutions are allowed, or you can say those solutions are possible, which is known as a state. Now came to our density of state. Density of state is the number of available energy states per unit volume corresponding to energy E. See, in EK diagram, we say that for a particular value of the K, there is a particular value of E. Okay, this is what we will study in our EK diagram. For a particular value of K, there is a particular value of E. When I calculated my density of state at this energy, then we get a particular result. When we calculate my density of state at this energy value, then I get some value of density of state. Okay, this means density of state is corresponding to energy E. That's why I use this line in my definition. Okay, now how we denote the density of state? Density can be denoted by rho or D. See, D of K, rho of E, D of E, or rho of K. These all are the way of representing the density of states. Here, what this K and what is the meaning of E? E and K define the band structure, or you can say EK diagram. Here K is the wave vector and E is the energy space, or you can say wave space, energy space. Wave vector is also known as propagation vector and it is related to momentum. These all are the points of EK diagram. How K is related to P? K is equal to H cross P. Okay. Now D of K into dk is the number of state between K and dk per unit volume of the material. See, I just drawing my EK diagram in this way. Suppose I take my this K value, then I get a corresponding energy E. Let I increase my K value by a small amount, say dk, then I get a corresponding energy dE. Okay, so number of states between K and dk, this colored portion is the space K and dk. Number of state between K and dk per unit volume of the material is D of K into dk. Okay. Similarly, when I see here, number of state between E and dE per unit volume of the material is dE into dE. Okay. Fine. Now, the energy value E depend only on the sum of squares of quantum number nx, ny and nz, not on their individual values. This is the point which we study in our dimension in one box or Sommerfeld model, where we came to know that for a three-dimensional box, energy will be depend on nx square, ny square and z square. Okay, so that's the same thing. Now let's construct a n space. Okay. When I join my nx, ny and nz, then I get a sphere. Okay. Here n shows a space which is the sum of square of nx, nz and ny. Okay. Now we know that energy values are positive. Here we take only the positive value of nx, ny and nz. Why I take only positive values? Because in this case we have a standing wave. I hope all you are aware of standing waves. In standing waves, when we take the positive values, when we consider the positive, then automatically the negative will be considered. Okay. When I take the only positive portion of this, when I take positive portion of this, then we have not a sphere. We will remain only of the octant, 1/8 portion of this sphere. This is the 1/8 portion. This shows only positive values. Okay. It looks like an octant. Okay. Now I take a sphere of radius n, and then I take a sphere of radius n plus dn. Okay. Fine. Now I take this portion. We will discuss about this portion. Fine. The number of states available within the sphere of radius n is equal to 1/8 into 4/3 pi n cube. Why? Because volume of a sphere is 4/3 pi r cube. Okay. Here radius is n, so we get 4/3 pi n cube. Why we multiplied our solution by 1/8? Because nx, ny and nz can take positive integers only. When we take positive values only, we came to a octant. Okay. Similarly, the number of states available within the sphere of radius n plus dn is 1/8 into 4/3 pi. Here radius is n plus dn, so n plus dn whole cube. Okay. Fine. Hence the number of state in the energy range dE. I want to calculate the number of states in only portion dE. How we get? If I minus E plus dE. Okay. Then it get cancelled out. We get the dE portion only. So what we did? We subtract our equations. By subtracting our equations and solving them, we get this: pi/2 into n square dn. Okay. By neglecting dn square and dn cube because they are very small. See, this is the solution of dE of dE. 1/8 and 4/3 pi is common from both the equations. N plus dn cube minus n cube. What is the formula of a plus b का whole cube? A cube plus b cube plus 3a square b plus 3ab square. Okay. Minus n cube and n cube get cancelled out. Dn cube is very small, that's why we neglect this. And dn square also we neglect this. What we will remaining of? 3n square dn and pi/6. Cancel out. So what we get? we get pi by 2 into n square dn. This is the same we see here, pi by 2 n square dn. Okay, this is our density of state, or you can say number of state in the energy range dE. Now from the Sommerfeld model, or you can say dimension in one box quantum free electron theory, we know that E is equal to n square h square by 8 ml square. So we get n square is equal to 8 ml square by h square into E. What is the value of n? I just rearrange this. Okay, n is equal to 8 ml square by h square raised to the power 1 by 2 into e to the power 1 by 2. By differentiating this equation, what we get, dn is equal to 1 by 2 8 ml square by h square to whole to the power e 1 by 2 into dE by e to the power 1 by 2. I just use the formula of x to the power n, which is equal to nx n to the power minus 1. Okay. Now put the value of n square and dn in equation number 1. What is our equation number 1? This is our equation number 1. So let's put, I just put the values of n square and dn. This is dn, this is n square. Okay, I just put these values and then just cancel out. See, here the power is 1, here the power is 1 by 2. 1 plus 1 by 2, I get the power of 3 by 2, else everything is same. This 1 by 2 into pi by 2, I get pi by 4. Okay, so our equation is pi by 4 into 8 ml square by h square to the power 3 pi by 2 into e to the power 1 by 2. Here is e, 1 minus 1 by 2, I get 1 by 2. Okay, d of e into d is equal to pi by 4 8 ml square by h cross into 2 pi. We know that h cross is equal to h by 2 pi. H cross is the reduced Planck constant and h is the Planck constant. I just put the value of h square here. Okay, else everything is same. Fine. Now next, what we get, dE of E into dE is equal to pi by 4 into 1 by pi cube. Here I take pi common. When I take pi common, 2 cancel out. What we will remaining of pi cube. Here 1 pi get cancel out, we remaining of 1 by 4 pi square. Okay, 8 ml square by 4 h cross square to the power whole 3 pi by 2 e to the power 1 by 2 dE, all everything are same. Okay, next we get d of e, dE is equal to 1 by 4 pi square 8 ml square by 4 h cross square 3 pi by 2 into e to the power 1 by 2 dE. Fine. Now just rearrange this. From where we get V, L cube is equal to V, volume. Okay, see here L, this is V. Okay, this is our required equation. Now we know that Pauli exclusion principle allow 2 electrons in each state, okay, with opposite spin. So number of quantum state available are multiplied by 2. See, Pauli's said that in a particular energy state we have 2 electrons with opposite spins, plus half and minus half. So the number of quantum states available are also multiplied by 2. These are states. Okay, these are, what are these? These are quantum states. These are also multiplied by 2. Okay, that's why we multiplied our equation by 2. What we get? D of E into dE is equal to V by, just cancel out 2 and 4. We get V by 2 pi square into 2m by h cross square to the whole power 3 by 2 into e to the power half into dE. Okay, this is our final required solution of the density of state. If you have any doubt regarding to density of states, then you can ask me in comment section.